Next topic is equipotential surfaces. Here equi means equal, that is same. Potential means electric potential, and the surfaces. It means equipotential surfaces are the surfaces at each point on which electric potential remains the same. Since electric potential at each point on an equipotential surface is same, potential difference across any 2 points on an equipotential surface will always be 0. Now, properties of equipotential surfaces. Since electric potential difference across any 2 points on an equipotential surface is always 0, the potential difference means work done in moving a unit charge from one point to another. So W, work done in taking a charge Q0 from one point to another on an equipotential surface will always be 0, and this implies W is equal to 0. It means work done in taking a charge from one point to another on an equipotential surface will always be 0. Also, electric field along equipotential surface E is equal to minus dV by dr, and if we are considering along the surface, then for any 2 point on the surface electric potential difference will be 0. Hence E is equal to minus dV by dr gives E is equal to 0. It means electric field along equipotential surface will always be 0. If electric field along the surface is 0, then what should be the direction of electric field? Then it means electric field must be perpendicular to equipotential surface. And if electric field is perpendicular to equipotential surface, then electric field lines will also be perpendicular to equipotential surface. Now third, electric field E is equal to minus dV by dr, and if we are having two equipotential surfaces, then for those two equipotential surfaces potential difference dV will be constant, because potential at each equipotential surface is same. Hence for two equipotential surfaces electric potential difference will be constant, and if dV is constant, then electric field will be inversely proportional to the separation between the surfaces, and hence in weak electric field, when E is less, dr will be more. Means in weak electric field the separation between equipotential surfaces will be more. In a strong electric field, then if E is strong, then dr will be less. It means in strong electric field equipotential surfaces will be closer to each other, and in a uniform electric field equipotential surfaces will be parallel and equidistant. Also, two equipotential surfaces will never intersect each other, because if two equipotential surfaces will intersect each other, then the electric lines of force produced by them will also intersect each other, and two lines of force can never intersect each other, because if they will do so, then at the point of their intersection there will be two directions of electric field, which is impossible, because a vector can have only one direction at a point. Now we will see the equipotential surfaces due to various charges and charge distributions. Say we are having a point charge, then due to point charge electric field is inversely proportional to square of distance, while electric potential inversely proportional to distance from the charge. Hence, as electric field from charge will decrease, the separation between equipotential surfaces will increase, and potential being inversely proportional to R, the points of same electric potential will lie on a spherical shell around the charge. Hence, equipotential surfaces due to a point charge will be concentric spherical shells, with separation between the shells gradually increasing because of decreasing electric field. Now, in uniform electric field, like the field produced by a thin infinite sheet of charge, equipotential surfaces will be parallel and equidistant. If we are having two thin sheets oppositely charged, then electric field between them will be almost uniform, while outside them electric field will be negligible. Hence, equipotential surfaces due to two thin oppositely charged sheets will be as shown by dotted lines. Now, for two opposite charges, electric field between the charges, say I want to find electric field somewhere here, then due to positive charge away from the charge, due to negative charge towards the charge, hence electric field in between the charges will be strong, while electric field outside them will be weak. Hence, the equipotential surfaces will be closer in between the charges, while outside them they will be away from each other. It means the shape of equipotential surfaces will be this type of shells. Now, in case of like charges, for two like charges, if I want to find out electric field in between the charges, then for first charge away from the charge, for second charge away from the charge, it means the fields due to two charges will be in opposite directions. Hence, electric field between them will be weak, while outside them electric field will be strong, because both the charge will be producing electric field away from them. Hence, outside the charges, the equipotential surfaces will be closer because of strong electric field, while within the charges equipotential surfaces will be comparatively farther. Hence, this type of shells will be obtained in case of equipotential surfaces due to two like charges. If electric field is gradually decreasing, then lines of force will be gradually moving away from each other, and in that case equipotential surfaces will be of this shape. The separation between the equipotential surfaces will be gradually increasing. But if electric field is gradually increasing, then the separation between equipotential surfaces will be gradually decreasing. Hence, for gradually increasing electric field, equipotential surfaces will have this type of shape. Now we will obtain an expression for kinetic energy attained by a charged particle when it is accelerated through a potential difference. Say we are having two metal plates, one positively charged, another negatively charged. Positively charged plate is at potential V1, while negatively charged plate is at potential V2. Then the potential difference across the plates V is equal to V1 difference V2, and we know that electric field between the plates E is equal to minus dV by dr, that is negative of potential gradient. Hence, the electric field between the plates E will be V1 difference V2 divided by dr. It means it will be potential difference V between the plates divided by distance between the plates, and distance between the plates this time we have taken as d. So instead of dr it will become d. Now electric field between the plates is V upon d. If we are placing a positive charge Q adjacent to positively charged plate, then electric field between the plates will exert a force on this charge in its own direction, and that force will be given by Q into E. This force will make the charge move towards the plate having potential V2. It means the charge will move from positively charged plate towards negatively charged plate, and in this process it will cross a potential difference V. So work done by electric field on charge W will be force into displacement. Force is F, displacement is D, so F into D. But what is F? F is QE, so work done will be QE into D. But from this expression, electric field into distance will become electric potential difference V. So this work done will become equal to QV. And we know that work done by electric field on charge will appear as the increase in kinetic energy of charge. Hence, kinetic energy attained by charged particle K is equal to work done W, that is QV. Thus, if a charge Q crosses a potential difference V favorably, then it gains a kinetic energy K given by QV. But if it crosses the potential difference V in opposite sense, then it will lose a kinetic energy equal to QV. If mass of charged particle is m and speed attained by charged particle is v, then kinetic energy can be given as half mv square. So half mv square will become equal to qv, and this implies speed attained by charged particle v is equal to under root 2 qv by m. If charged particle is an electron, then charge q will be 1.6 into 10 to the power minus 19 coulomb and mass m 9.1 into 10 to the power minus 31 kg. And if we will be replacing q by e, then kinetic energy gained by electron accelerated through a potential difference v will be e into v. Now E means electronic charge, V means potential difference, and it means electron into volt. Electron volt forms a new unit of energy, and 1 electron volt is defined as the energy gained or lost by an electron in crossing a potential difference of 1 volt. If a potential difference of 2 volt is crossed by an electron, then kinetic energy gained or lost by it will be 2 electron volt. If it crosses a potential difference of 5 volt, then kinetic energy gained or lost by it will be 5 electron volt. Thus, speed gained by electron V will be 2 into charge of electron 1.6 into 10 to the power minus 19 upon mass 9.1 into 10 to the power minus 31. Decimal is cancelled for both 1.6 and 9.1. Hence, it will become 2 into 16 into 10 to the power minus 19 divided by 19, 1 into 10 to the power minus 31 multiplied by potential difference V. If we will solve it, it will come out to be approximately 5.93 into 10 to the power 5 root V. It means directly we can use for electron speed gained V is equal to 5.93 into 10 to the power 5 into under root of potential difference through which electron is accelerated. If you think this video is of any help for you, then please share it with your friends so that they may also be benefited by it.